This is Dr. D. Govardhan, Professor and Editor, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, covering the determination of center of gravity of bodies, lines and arcs. The center of gravity of solids or the plane figures or the lines can be determined by using the principle of moments. According to the principle of moment or the Wagner principle, the moment created by the resultant force at any point is equal to the algebraic sum of the moments created by its components. Here let us consider a figure which is kept in the xy plane as shown in figure. Let it be divided into some number of segments having masses m1, m2, m3 as shown in figure. The weight of each segment is m1g, m2g, m3g and so on. The total weight of the object is equal to capital M into G, where capital M is representing the sum of the masses possessed by each segment. Then according to the principle of Wagner principle, the moment created by the resultant force, that is the total weight of the body, that is mg into xc is equal to m1 x1 plus m1 x1 g1 plus m2 g x2 plus m3 g x3 and so on. Since g is the common term, so x is equal to sigma mx divided by m. Similarly, yc is equal to, that is y coordinate of the centroid is equal to sigma m by capital M, where capital M representing the total mass of the body, which is equal to m1 plus m2 plus m3 and so on. Okay, for the two-dimensional objects, xt is equal to a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3. Similarly, yc is equal to a1 by 1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. By assuming that the thickness of the object is uniform. For the one-dimensional problems, by assuming the area of the cross-section remains constant, then the modified equation of above, it can be written as now, xc is equal to L1 x1 plus L2 x2 plus L3 x3 divided by L1 plus L2 plus L3. Similarly, yc is equal to L1 y1 plus L2 y2 plus L3 y3 divided by L1 plus L2 plus L3. Okay, by using these fundamentals, we are determining the center of gravity or the centroid of plane figures, lines as well as the three-dimensional objects. The center of gravity of symmetrical sections. While determining center of gravity of symmetrical section, the reference line is always required to represent the position of centroid or center of gravity. So the reference lines generally treated as symmetrical lines. But when the object is unsymmetrical about the vertical and horizontal lines, the horizontal line which is passing through the bottom of the figure is represented as x-axis, and the vertical line passing through the extreme left of the object is treated as a y-axis. By using these two lines, reference lines, we can locate the position of centroid. Center of gravity of solid bodies. Here we are determining the center of gravity of hemisphere, cylinder, right circular, solid cone, etc. Just by using the principle of xc is equal to m1 x1 plus m2 x2 plus m3 x divided by m1 plus m2 plus m3. This is what we discussed earlier. Since if the object is that is I am taking here now x is equal to m1 x1 plus m2 x2, only two elements I am taking, m1 plus m2. If the density of the material is same now, that is the composite figure, if it is made up of same materials, it can be written as now rho v1 x1 plus rho v2 x2 divided by rho v1 plus rho v2. Simply it can be written as v1 x1 v2 x2 divided by v1 plus v2. This is representing the position of the centroid, that is x coordinate for the given solid. Similarly, for yc is equal to, we can take it as v1 y1 plus v2 y2 divided by v1 plus v2. So, when we are determining the centroid of composite solids, we have to divide that object into some number of segments, like it in the form of hemisphere or cylinder, right circular, solid cone and so on, and determine the volume of each part and represent the reference axis. The reference axis, if the object is symmetrical, the symmetrical line is treated as axis for the reference. Otherwise, the line which is passing through the bottom of the figure and the extreme left are treated as the reference axis, vertical as well as the horizontal lines respectively. Now I am taking the volume of the cylinder is equal to pi r square h, where r is representing the diameter radius of the base circle and h is representing the height of the cylinder. Similarly, volume of the hemisphere is equal to 2 by 3 pi r cube and volume of the right circular cone is equal to 1 by 3 pi r square h. Okay, these are the fundamentals we have to remember while solving the problems. If the density of the material is not constant for the composite figure, if it is made up of different materials, the modified equations for the x is equal to, from the equation m1 x1 plus m2 x2 divided by m1 plus m2, we can take, if the material is different, to rho 1 v1 x1 plus rho 2 v2 x2 divided by rho 1 v1 plus rho 2 v2, we can take it now. Similarly, yc is equal to rho 1 v1 y1 plus rho 2 v2 y2 divided by rho 1 v1 plus into rho 2 v2. That means earlier we have taken rho is a constant, hence it gets cancelled in denominator and numerator. But if the material is different for each part, then you have to add the corresponding density to each volume. The obtained values are known as the coordinates of the centroid. Here I am taking one problem now. A solid body formed by joining the base of right circular cone of height h to equal base of right circular cylinder of height h, small h. Calculate the distance of the center of mass of the solid from its plane face when h is equal to 20 mm and small h is equal to 120 mm and small h is equal to 30 mm. Here it is given, this is nothing but representing the orthographic projection of composite figure, which is made up of right circular cone. This is known as a right circular cone, having height is equal to 120 mm. Base diameter, here r is given, the radius of the base circle, small r. Now, it is kept to just over the circular cylinder of height h, having the same base diameter. That is the radius is equal to small r. Now you determine the position of the centroid of a composite figure. If we observe this object clearly, it is symmetrically with respect to the vertical lines. Hence, the axis, that vertical line is represented as y reference to determine the position of centroid. This is known as position of vertical line now. It is treated as a y-axis now. The line which is passing through the bottom of the figure, it is represented as a x-axis and y-axis now. Now for each element, by using the principle of xc is equal to v1 x1 plus v2 x2 divided by v1 plus v2, where v1 and v2 representing the volume of this part 1, that is cylinder, and 2 right circular cone, and x1 x2 is representing the position of their centroid with respect to the reference line. Now for the first figure, now it is in the form of cylinder having height is equal to 30 mm, and the radius of the base circle is equal to small r, hence v1 is equal to pi r square h. For the cylinder, pi r square h, pi r is given, it is a constant, is given like that only. H is equal to 30 mm, and simplification we got to 30 pi r square mm cube. It is representing the volume of the cylinder. Similarly, for the right circular cone, volume is representing 1/3 pi r cube, which is equal to pi by 3 r square into h. 1/3 pi r square, h is representing the volume of the right circular cone. Pi by 3 r square is the constant is given. H is equal to height of the cone, which is equal to 120 mm. According to the figure, it is represented. Hence, on substituting the values, we got to 40 pi r square mm cube is representing the volume of the right circular cone. And y2 is equal to, y1 is representing the position of the centroid for the cylinder. It is at a distance of half of it. Height is given 30 by 2, hence it is equal to 15 mm. Similarly, the position of the centroid for the right circular cone is representing, here it is at a distance of h by 4 from its base. That means from the bottom position, it is having 30 plus h by 4 now, which is equal to 30. 120 is representing h by 4, it is equal to 30. So, when I get cancel, the remaining values is equal to 60 mm is representing the position of y2. That means the position of center of gravity for the right circular cone with respect to its with reference to the reference line which is passing through the bottom of the composite figure. And substituting the values of v1 y1 and v2 y2 in equation to get the centroid position, that is yc is equal to v1 y1 plus v2 y2 divided by v1 plus v2. So substituting these equations, v1 is equal to 30 pi r square into y1 is equal to 15 mm plus the second one 40 pi r square, that v2 is equal to, and y2 is equal to 60 mm divided by v1 plus v2, that is 30 pi r square plus 40 pi r square now. Since pi r square is the common terms, it gets cancelled in denominator and numerator. On simplification, we got 2850 divided by 70, which is equal to 40.7 mm. This is the position of the centroid with respect to the bottom of the composite figure. So it is somewhere 30 plus 10 it is there. This is the position it is there now. this distance is equal to, here it is representing the 40 mm from its base now, base of the composite figure. Now one more problem I am taking. A body consists of right circular solid cone of height 40 mm and radius 30 mm of the same materials. Is placed on a solid hemisphere of radius 30 mm of the same material. Find the position of center of gravity of the body. A body consists of a right circular solid cone of height 40 mm, radius 30 mm, placed on a solid hemisphere of radius 30 mm of the same material. That means the given data is now, here it is given. The hemisphere is given having the radius is equal to 30 mm. Yeah, I think yes, it is the one now. Again, a right circular cone with the same diameter they kept over it now. So we have to determine the center of gravity of this composite figures now. Let hemisphere is treated as one object and 2 is representing the right circular cone. Since the object is symmetrical about the vertical lines, this vertical line is treated as y-axis and the position of here it is known as the x-axis and so on, bottom figure. Now the volume of the first hemisphere is equal to first figure. It is equal to 2 by 3 pi r cube, which is equal to 2 by 3 pi r cube is equal to radius is equal to 30 mm is given. And substituting the values we got to 18,000 pi mm cube the volume of the hemisphere. The position of centroid for the hemisphere is given 3r by 8 from its base position now. But when we are measuring from bottom position, D position, the values is 5r by 8, which is equal to 5 into 30 by 8, it is equal to 18.7 mm now. Similarly, for the right circular cone, the volume of the right circular cone is equal to 1 by 3 pi r square h. Okay, pi by 3. R is equal to again 30 mm is given, 30 square. The height of the right circular cone is given 40, and so 40. On simplification, we got to 12,000 pi mm cube now. Now, y is equal to the position of the centroid for the right circular cone is equal to, from the bottom position, this is given 30 mm plus here is given h by 4, that is the position is somewhere here h by 4 now. H by 4 is equal to how much it is now? 10 now. That is 30 plus 10 is equal to 40 mm. That is yt is equal to 30. That is nothing but representing the radius of the hemisphere plus the position of central gravity of right circular cone is equal to h by 4. That is 40 by 4, which is equal to, here will get cancelled, the remaining values is equal to 40 mm. The distance between the central gravity of the body and bottom of the hemisphere, that is d is equal to, yc is equal to v1 y1 plus v2 y2 divided by v1 plus v2. And substituting the values now, v1 is equal to 18,000 pi into y1 is equal to 18.75 plus v2 is equal to 12,000 pi into 40 divided by 18,000 pi plus 12,000 pi. Since the pi remains constant in all terminology, on simplification we got this value is equal to 27.3 mm. This is representing the position of the centroid. It lies approximately at this position. That is, here 27.5 somewhere it is there. Okay, this is the required answer. This is the procedure generally used to determine the CG of the solids. And one more figure now. A right circular cylinder of 12 centimeter diameter is joined with a hemisphere of the same diameter face to face. This is known as a right circular cylinder. The radius is given 120 mm, that is 12 centimeter, and height is given small h. It is given like this. It is joined with the hemisphere of the same diameter face to face. That is, this is known as a hemisphere now. It is given. That is, hemisphere is given now, 60 mm. Diameter is given now. Radius is given 60 mm. So that the center of gravity of the composite sections coincide with the plane and joining the two sections. The density of the material of the hemisphere is twice that of the material of the cylinder. Here, what is the required now? Find the greatest height of the cylinder. This height is equal to how much is required now. So that the center of gravity of composite figure lies coincide with the interface of the composite figure now. The density of the material of the hemisphere is twice that of the cylinder. Assume, since if we observe this object, it is symmetrically with respect to the vertical line. Hence, this y-axis is representing the position of y-axis or vertical reference line, and bottom figure is representing the position of x-axis. Now, let us assume h is equal to height of the cylinder. Now, first I am taking red circular cylinder now, this figure. The volume of the figure is equal to, since here the density is not the common for the both the cylinder as well as the hemisphere, the equation it can be written as now xc is equal to, we can take it as m1 x1 plus m2 x2 divided by m1 plus m2, where m1 is equal to rho 1 v1 x1 plus rho 2 v2 x2 divided by rho 1 v1 plus rho 2 v2 and so on. This equation is applicable for determining position of the center of composite figure. Now, in this case, here weight of W1 is equal to, here the density is given now, it is equal to rho 1 pi by 4 into d square into h. That is the volume multiplied by the density. It is representing the m1 values. That is the rho 1 into, here m1, that is the mass of the right circular cylinder is equal to, m1 is equal to rho 1 into pi by 4 d square into h. Here rho 1 is given now, pi by 4, d is equal to, here the diameter is given 120 mm. So, 120 square into h. H values we have to determine, and simplifications we got to 3600 rho 1 pi h now. Now, according to our problem now, the density of the hemisphere metal is the twice that of the cylinder. Hence, rho 2 is equal to, we can write it as 2 into rho 1. That is the weight of the W2 is equal to, hemisphere is equal to rho 2 into 2 by 3 r cube. 2 into rho 2 is equal to, we can take it as 2 into rho 1, 2 by 3 into 60 cube now. On simplifications we got to, which is equal to, on simplification we got to, this value is equal to 2,88,000 rho 1 into pi now. Yt is equal to, it lies at a distance of 5r by 8 from the base position now, where r is representing the radius of the hemisphere now. 5 into 60 by 8, which is equal to 3000 divided by 8, 37.5 mm now. The distance of the center of gravity of the combined body from the bottom of the figure, it is given by Yc is equal to m1y1 plus m2y2 divided by m1 plus m2 now. Here W1 is given just weight now, that is the rho is, that is G is a constant for the both the materials, hence get cancelled now. We can take it as m1y1 plus m2y2 divided by m1 plus m2. Since the Yc is, that is the position of centroid lies at the intersection of the two bodies now, which is at a distance of 60 mm from the bottom of the figure. Hence, Yc is equal to, we can take it as 60, which is equal to the m1y1, that is 3600 rho 1 pi into h plus w2 into h by 2, that is a 60 into h by 2 plus 1 lakh is given W2 into Y2, that values is given now, which is equal to 1 crore just 80 lakhs now, divided by 3600 H plus 2 lakhs 88,000 now. So from these relations now, just by bringing the H values in one side as well as the coefficients on the other side now, we got 1800 H square is equal to, it is equal to 64 lakhs 80,000 now. So H is equal to under root of 64 lakhs 80,000 divided by 1800, which is equal to under root of 3600, or it is equal to 60 mm. That is, the height of the cylinder should be equal to 60 mm. Then only the center of gravity of that composite figure lies with the plane, which is the intersection of both the cylinders.
Like, share and subscribe. Hit the bell icon for more updates.